Welcome back. Today we're going to talk about Reconstruction attacks. The last time we spoke informally about privacy violations, but this time we'll be a bit more precise and formal so that we can really see what type of attacks are sort of a general framework for attacking in various settings. So in today's lecture, we're not going to really talk about what it means for an algorithm to be private, but we'll talk about what it means for an algorithm to be non-private. In particular, what it means for an algorithm to be blatantly non-private. So, like, you can maybe split hairs about whether one thing is private versus some other thing is private, but we're going to have such a blatant form of non-privacy in this lecture such that there's really no ifs, ands, or buts about it. It's a non-private algorithm. So the sort of centerpiece of today's lecture will be this paper of Dinur and Nassim from 2003, which is kind of seen by many to be one of the sparks of differential privacy. So differential privacy wasn't actually introduced until a paper in 2006, but this paper really set the stage for it. And in particular, section 4 of that paper of Dinur and Nassim from 2003, which was jointly written with Cynthia Dwork helped with section 4 as well. She contributed to that section. That section really has what you can see as the first steps towards differential privacy. Like, after you've seen differential privacy, you can look at it and see that this is kind of where it all started. Yeah, we're not going to get into section 4 of this paper today. It'll be more focused on the other half of it, which is the attacks. But yeah, once you know differential privacy, I think it's an important thing to look at that paper to understand what it looked like as kind of like an archaeological search to see where the ideas came from. There's some differences from it. In particular, it focuses on computationally bounded adversaries rather than nowadays we're more into query bounded adversaries. It focused on binomial noise instead of, say, Gaussian or Laplace noise, stuff like that. But still, the core of it is there somewhere. But anyway, yeah, today's going to be about reconstruction attacks. First, we're going to start with sort of following the presentation of a paper by Garfinkel, About, and Martindale, sort of showing how in a census type environment, you can reconstruct the data set from aggregate statistics. This is sort of in a noiseless setting. The next one is looking at a noise setting. Suppose the curator, whoever is providing you statistics based on a data set, gives you some noised answers. Well, under what circumstances can you recover the private information? That's what the Dinur and Nassim attack focuses on. And the final one is a very recent result by Cohen and Nassim. And this provides a sort of more practical approach to this, in the sense that it's really an attack on a production system, which shows that, even though this paper came out 17 years ago and was primarily theoretical, it shows that the ideas there are really useful and can actually help in reconstructing databases in practice. So we'll build our way up to that, but starting first, we'll begin with census reconstruction. So the setup. So today we're going to be presenting based on the presentation of Garfinkel, About, and Martindale. And if you're curious, we're going to go over it very sort of a high level, but I recommend thoroughly reading their article to get really the details and how you'd actually execute something like this. So what is the setup? The setup is a census type setting. So what is a census? A census will go to pretty much each person in some population and ask them for some demographic type data and questions about them, trying to count how many people there are and sort of understand various statistics about the data set. For example, maybe you go to each person, you collect the microdata, which has things such as an individual's age, their sex, their race, and perhaps more, though we're only going to be concerned with these features for today's presentation. And in particular, to really simplify it, we're going to work in a simplified model where race is either, say, black or white, and where sex is only, say, either male or female. So imagine you had a bunch of data points of this form where it just collected individuals' age, sex, and race, and it listed all of them. That would be what's known as the microdata. This is generally considered to be sensitive in nature, but it's really sort of the raw data. In particular, legal regulations would prevent a census-type application from releasing the raw microdata in several cases, so we really can't do that. Instead, what they do is they release aggregate statistics for, say, a block, or maybe a city or a county or something like that. And this is the type of statistic which is released to the public for that type of information. So let's take a look. You can see it over here on the right. This is an example of what an aggregate would be. This is an example for just a single block, which has, say, 7 people in it total. So what are we doing here? We have certain things. We can see that, first of all, this does not immediately let us read off, how many people, like the individual statistics of people. Like, given these males, there's 3 males, but we don't know exactly how old they are, what race they are, etc. And in particular, there's some statistics which have been suppressed, in particular these ones that are marked with a D. These are ones where there are either 0, 1, or 2 people who fall into this category, so for the sake of their privacy, the information has been hidden. Let's take a look at one example. For example, we can see that total there's 4 Black or African American individuals in this example. 3 of them are female, so therefore we can infer that only 1 of them is male. And if we had either the median or mean of this one individual, it would exactly reveal their age and thus violate the individual's privacy if we consider this sensitive information. So this is a privacy violation if we did report it here, so that's why it's suppressed. But generalizing this observation, what did we do? We basically took one statistic, seeing how many males and females there are, and then subtracting out how many females there were. This kind of told us something about how many males there are. Stated another way, what we're going to be able to do is, maybe giving you a sneak peek of the future, we're going to be able to make constraints based on how all of these different statistics interact with each other. And based on that, we'll be able to reconstruct a set of microdata which agrees with it. In particular, there's certain redundancies which will allow us to figure out which possibilities are feasible and which ones aren't. And given sufficiently many constraints, similar to this, then we're going to left with only one feasible microdata, which is the true one. Okay, but we're getting a bit ahead of ourselves. Let's take a closer look at say, statistic 2b, just to start with something concrete. Okay, so we're told that there are 3 males, and their median age is 30, and their average age is 44. Okay, so let's let their ages be without loss of generality. We're going to say their ages are A, B, and C, because there's 3 individuals, so let A, B, and C be their ages, where, like, in particular, let's say, like, A is less than or equal to B, is less than or equal to C. Put them in non-decreasing order. So what can we say about their ages based on the info we have here and what we generally know about humans or males? The first thing we can say is, okay, let's assume, so let's write this as, say, the constraints that we have. The first thing we know, for example, is potentially this is a census which only takes whole number ages. You can be 0, you can be 1, you can be 2, but you can't be 1.5 or something. Okay, so that's just a starting point. We're going to say that we know each of these are whole numbers. The second thing we're going to know is, what can we say about the ages and where they lie? Well, first thing, like I said, each age is going to be greater than or equal to 0. You can't have a negative age. And the other thing we can say is also, just using historical data that we know sort of a priori without even looking at this data set, is that I'm going to say that all of the ages are less than or equal to 125. The oldest recorded person ever lived to be 122 years old, so we can say with relative safety that there's only 125 different, each person will only live to be 125. Okay, so let's suppose this is all we had. Then what can we say about the total number of combinations of A, B, and C? Well, there's actually quite a few options. How many are there? There's something like, okay, this is an exact calculation, but say A can be any integer between 0 and 125, so that's like roughly that's 126 options. And then B is going to be similarly having 126 options, and C should also have 126 options. So it's not exactly this because of the fact that I place them in sort of non-decreasing order, so there's some things which are not allowed. But roughly speaking, there's 126 cubed options, which is somewhere in the ballpark of 300,000. So right now it seems pretty private in the sense that based on just these numbers, the fact that there's 3 ages, there's like 300,000 different possibilities, and we have no idea which one's the right one. However, we know a lot more than this. We also know we haven't actually used any of this data in this aggregation table. Let's see what we have there and what we can do with it. So what do we know about this? We know that, first of all, the median is 30. Well, that implies that exactly one thing, because there's 3 numbers and we know the median of them is 30. That tells us that B is equal to 30. Okay, so that's one thing we can say. So that narrows it down a bit. Maybe that makes it more like on the order of 126 squared, let's say, because the middle number is sort of fixed now. But that's not all we know. We also know that the average value is 44. So that tells us the following. 1/3 times A plus B plus C is equal to 44. And in fact, substituting in the fact that we know B is equal to 30, this implies that, in fact, A plus C times 1/3 overall is equal to 34. So now we have far fewer choices and far fewer options for what A, B, and C can be. For example, now based on this, then we could say let one possible solution, which you can verify for yourself, is say A equals 0, B equals 30, and C is equal to 102. This is one possible set of ages which would satisfy this constraint, which you can check for yourself. That's one option, but actually there's a total of 31 different options. For example, you can also do A equals 1, B equals 30, C equals 101, and so on. And in fact, all of these cases are enumerated here. Here they have, I guess they have 30 different possibilities because they didn't consider, this is both of these figures, by the way, are from the article of Simpson, rather Garfinkel et al. But here they have 30 options. There's really 31 options if you consider if you consider 0 to be a valid age. So the point is that somehow these 2 constraints of the median and the mean, they allowed us to narrow down the number of possibilities of ages from 300,000 all the way down to just 31 different options. This gave us significant information about 3 of the individuals in our data set, and we only used a single one of these statistics. Like, remember, there were all these other ones, 1A, 2A, all of these other things. We didn't even use them yet, so there's still a lot more narrowing down that we can do. So an attack in the settings sort of takes the following form. It's rather simple, I guess, in the sense that all you do is you generate constraints which are implied by the statistics. So, for example, 2 constraints rather that we generated are, say, B equals 30, and this 1/3 A plus C is equal to 34. So simply just generate all these constraints. And then the second step of any attack is find a feasible point. So, like, you might be thinking here, okay, there's a lot more than 31 feasible, there's a lot more than one feasible point, there's 31 options. So, like, how do we know which one of these choices is the right one? But the thing is, imagine you have all these statistics. It's possible to define, statistics, it's possible to define constraints based on all these statistics, which narrow it down rather rapidly. In particular, if you take all the constraints implied by these ones, by all these aggregate statistics here, including potentially things here, for example, since this is suppressed, we know that either 0, 1, or 2 people under 5 years old, and so on. But essentially aggregating, like putting together all the constraints that are implied by this table and finding a feasible point, that gives us only a single feasible point, which in particular corresponds exactly to the true microdata. Now, there's some things I haven't mentioned here. For example, like I just said, generate constraints. We kind of talked about how to do that. But how do we find a feasible point? This is kind of hard, and it's also kind of easy. What do I mean by it's hard? I mean, this type of problem is hard in the sense of NP hardness. Because we were working with integer constrained values, we have to do things like integer programming or stuff like that. Which is in general, theory speaking, NP hard to solve. However, on the other hand, in practice, this is actually not super bad to solve. In particular, there's SAT solvers, which are very highly optimized. So in case you're not familiar with what SAT solvers are like programs which can solve a satisfiability constraint problem. This is one of the most classic problems in computer science. Which is well known to be NP hard, perhaps the archetypical NP hard problem. But the thing is, in practice, it's actually a fairly easy problem. We have programs and competitions dedicated to solving these very, very efficiently, and it seems like in practice these are not too bad. And in particular, encoding these type of constraints as a SAT problem allows us to find the right answer fairly quickly. So that's one way of solving it. Also, like I said, these are really integer programs, which, we actually have algorithms for solving this pretty efficiently. Sorry, not necessarily algorithms, but heuristics, which seem to solve cases in practice fairly quickly. So it seems like these are solvable. In particular, this solver, using a SAT solver on this small example, was able to solve it in 0.1 seconds or even less on just a regular laptop computer. So this is all fun and games. This is this seems like, okay, you can attack this tiny little instance with 7 people. That's not a big deal. But let me comment, this is like a real attack in the sense that the individuals I mentioned here, Garfinkel, Abboud, and Martindale, they actually work for the US Census. And they were able to execute the US Census in general was able to execute an attack against itself. In particular, they were able to basically take the aggregate statistics that they released publicly, and they were able to perform this reconstruction attack to create some sort of microdata. So they found a feasible solution, and they found some microdata which was consistent with the aggregate statistics. So they took this microdata and they matched it against the true microdata, and they found the following. They found that 46%, that is roughly 150 million Americans, their data was matched exactly by this microdata that was reconstructed from the aggregate statistics. More generally speaking, if you allow them a little bit of leeway, suppose you allow them to get a person's age up to plus or minus 1 year, in that case, they managed to reconstruct the data for 71% of the population. So this is even more people, 200 million plus people's microdata was able to be reconstructed using this method. So if you remember from last lecture, this is, okay, you have this type of data, but this doesn't really tell you, their name or anything. Perhaps that's not even collected in this survey. But they were actually able to do linkage attacks, similar to how we described last time. In particular, recall that a linkage attack is where you find data obtained from another source and try to match it up with the recovered data. So essentially, by relying on some commercial databases, which maybe they got for free or they were able to buy, they were able to match up that database and connect names and identities to this reconstructed microdata. And they found that this type of linkage attack allowed them to correctly re-identify, say, over 50 million individuals in the United States. So this was a huge attack and far more effective than previously done. Like previously, the U.S. Census had tried to attack their own data just to see how private is it, and they weren't able to. But using this method, they were actually able to do it. So there's what's known as a tutorial. It's a tutorial by John Aboud, which I link on the website. And this sort of describes, their process and how many, and some more quantitative numbers about how well they were able to attack it. So yeah, this has kind of raised some red flags because, like I mentioned, the U.S. Census by law is mandated to ensure that they protect individual privacy of individuals who participate in the U.S. Census. So simply, they don't have the luxury of just doing what they did back in 2010. Now that they know about it, they're mandated to try to protect against this type of attack. And this has led, in particular, to the adoption of differential privacy in the 2020 census. So this is mired with a lot of the 2020 census has been mired with a lot of controversy. So it remains to be seen, and it's going to be very interesting to see how different the differential privacy experiment turns out this time, and if it will be able to provide high quality data that really social scientists or people who use this down the road really require. That's going to be really exciting to see. That's it for this example about a census reconstruction attack. Next, we're going to move on to Dinur Nassim database reconstruction.